Hi everyone, I'm Theophanis Tsandilas from the Université Paris-Saclay in India. I will present our CHI paper Gestural as a computation optimization problem. This is joint work with Pierre Dragicevic. Gestural studies are commonly used to look for intuitive mappings between user input and computer actions. The method became extremely popular following the work of Robrook, Morris, and Wilson on surface gestures in 2009. Since then, more than 200 gestural studies have been published. In a gestural study, participants are prompted with reference or the effects of actions. This is a referent and this is the effect of an action. Then they perform signs that cause those actions. But let me first clarify some terminology. A study collects descriptions of gestures. In my example, the description is a video recording that captures the gesture, while a sign is a label or symbol that classifies the gesture description. In my presentation, I will assume that all recorded gestures already have a sign. Now, let's consider a set of reference, 20 participants and their sign proposals. Our goal is to use this data to find a good set of mappings between signs and reference. Or even better, we want to find the best possible mappings. But what is best? We need a metric for comparing different mappings, or in other words, we need an objective function. The quality measure that we can use is guessability. Guessability was described back in 2005 by Robrook and colleagues. We can express it as a probability. The probability that a novice user will be able to guess and perform a correct gesture to activate a referent without prior learning. The authors also describe a heuristic for creating mappings that maximize guessability, and many later studies have used this heuristic. Unfortunately, the method has evolved very little since then. Often, authors combine a mix of subjective design criteria to infer sign vocabularies based on their data. I will highlight 5 key problems, and for each I will summarize our approach. Problem number 1. The guessability measure is rarely or never used in practice. A review of more than 200 studies between 2009 and 2019 shows that agreement measures largely dominate the analysis of gestural elicitation results. An agreement is commonly presented as an indirect measure of guessability. We argue that agreement metrics cannot be used to compare alternative mappings, so they are not appropriate for optimization. So we bring attention back to the original guessability measure. Second problem. It's easy to verify that Robrook's heuristic is not optimal. Consider this matrix that shows the distribution of participant sign proposals for 2 referents. The heuristic will map the sign A to the first referent and sign C to the second. If we calculate the guessability of these mappings, we find a score of 32.5%. But if we look more carefully, we can find a better solution, this one here, with a clearly higher guessability. We frame gestural elicitation as a combinatorial assignment problem. In the most common instance of the problem, its referent is mapped with exactly 1 sign, and each sign is mapped to at most 1 referent. For this case, we show how to use the Hungarian algorithm to maximize guessability. Problem number 3. Many authors use ad hoc analysis strategies. For example, they inspect the data to decide about how to produce mappings without conflicts, or to group gestures together. Such strategies present 2 main problems. First, they are subjective and hard to reproduce, but they also increase the risk of overfitting to the patterns that the investigators observe in the data generalize. To deal with this problem, we introduce a formal method for expressing custom design constraints as integer programs, a special type of linear programs. Given a set of reference and a set of observed signs, the approach enables the designers to map a referent to a group of related signs or map selected signs to multiple referents. Since we can computationally define the problem, not only can we optimally solve it, but we can further cross-validate the result to evaluate overfitting. We apply the leave one out cross-validation method. Each time we remove a participant from our training set and then use this participant's data to evaluate the optimal vocabulary that we found. Problem number 4. Our goal is to create a gestural vocabulary for the larger population of users. Ideally, we would like to elicit gestures from all these users and optimize based on all this data. But in practice, we collect data from a small sample of users, and the sign mappings that we derive maximize guessability only for this group of users. So to what extent are these two sign mappings similar or different? To assess but also to communicate the uncertainty of optimal sign mappings, we apply the bootstrap method. The idea is that instead of only running optimization once, we repeat it a large number of times by resampling the original sample. This way, we evaluate the variability and robustness of our sign vocabulary. Here, we apply the bootstrap method on the dataset of Bailey and colleagues. For each referent, we show a set of alternative signs together with a percentage. We can informally view it as a measure of confidence that the sign will be optimal if we run the study on the full user population. For this reference, there is a lot of uncertainty about which sign is the optimal one. For this reference, in contrast, we can be confident that we have the optimal sign. Problem number 5. What is a sufficient sample size? Villarreal, Narvaez, and colleagues report that 20 participants is the most typical choice, while 49% of the studies report less than 20 participants. But these choices are not based on any theory or any empirical evidence. How reasonable are they? We get inspiration from machine learning practice. We apply a learning curve method to evaluate how the training and cross-validate guessability scores converge as the sample size increases. In this example, we expect that the unknown population guessability will be somewhere around these two curves, but we can also predict the expected guessability error and decide whether it's worth recruiting additional participants. For a detailed presentation of our methods, we invite you to check our project page at GitHub. We provide our code, but also 2 case studies that explain and demonstrate our methods step by step for 2 real datasets. Thanks for your attention.